Okay. So yesterday we went through the introduction about the stress analysis on homogeneous ground, and we have went through one example about the estimation of the deflections within a load, within a circular load applied to the homogeneous ground. And then we actually have the formulas to identify the vertical deflections at any point in the ground. This is actually applied for the flexible pavement. But if we are talking about a rigid plate, which is placed on the top of the homogeneous ground, then we should have should also know how we're gonna estimate the vertical stress or vertical deflections behind the rigid plate. And these two figures, the figure here actually shows the clearly show the difference between the flexible and rigid plate. If it's in a flexible plate, for example, for the asphalt concrete layers, the load applied, if then the load applied to the AC layers, there is a significant deformation or displacement about the rigid plate, the flexible plate, and it will observe very large deflections at the center line of the contact area. And based on our previous analysis, we can find that the maximum deflection will be at the surface of the pavement, which can be represented as this equation, 3/2 times Q times A divided by E. But for the rigid plate, it's a little bit different. We define a rigid plate because the plate is rigid and it's able to support a very large load. And you will almost does not observe any deformations or deflections about the plate. Instead, the deflections only applies to the subgrade or to the homogeneous ground as a subgrade. And with that, we can actually estimate the deflections of the within a given load for the rigid plate, and explore the relationship between the deflections from the flexible plate and rigid plate. And first of all, for the rigid plate, we can find out the deflection, the stress at any depth. So at any contact area, at any distance. Sorry. So R is the distance to the center line. And this one will equal to Q, that will be the average stress or the pressure applied to the rigid plate. And usually for the rigid plate, the pressure will not be uniformly distributed. You can find out the distribution in this figure. It will have a very large value on the sides, and the value will be very small in the center. And this equation shows the distributions of the stress or the contact pressure under different locations of the rigid plate with respect to the distance to the center line. And then you can calculate the deflection at the applied to the subgrade or to the homogeneous ground with this equation, and that would be the Q times A divided by 2E times pi times 1 minus mu square. Mu is the Poisson's ratio. And if we do the comparison about the deflection, at the maximum deflection of the flexible plate, you can find that for the rigid plate, the value is just about 0.79 of the maximum deflection applied to the flexible plate. And this equation, this coefficient actually shows the relationship between the deflections of the rigid and the flexible plates. And also it indicates that usually for the rigid plates, it can have the better support. It will result in the smaller deflections to the pavement, to the subgrade layers. So that's the relationship. And then I'll go through one example to see how we can calculate the deflections of the with the rigid plate, and how we're going to use in the equation to determine the elastic modulus. In this problem, we assume that there's a plate. We are conducting the plate load test, and the plate is the rigid plate, and the diameters is 12 inches, and the load, the total load applied is 8,000 pounds, and we also know the deflection, the actual deflection observed from the field is 0.1 inches, and we want to find out what's the modulus of the elasticity for the subgrade. So based on these assumptions, we can first identify the radius of the contact area. So the diameter is 12 inches, so radius will be 6 inches. And also we know the load applied to the plate is 8,000 pounds. And the deflection, which will be deflection of the rigid plate, is 0.1 inch. And the value of Poisson's ratio mu is 0.4. And with that, we can then recall the formula of the deflection for the rigid plate. So we have W equal to Q times A divided by 2 times E times pi times 1 minus mu square. And here, Q is the contact pressure. So in this case, we can get a Q equal to the load divided by the area of the plate. So that is P divided by pi times A square. And for this specific situation, we have P equal to 8,000 and A is 6 inches, which will give you the contact pressure as 70.74 psi. And then in the equation to estimate the deflection of the rigid plate, we know the value of the deflection. We calculated the contact pressure. We know the radius. We also know the Poisson's ratio. So we can derive the formula for the elastic modulus. So that is Q times A divided by 2 times W times pi 1 minus mu square. By assigning all the values there, 70.74 times 6 divided by 2 times 0.1 times pi 1 minus 0.4 square, which will give you the estimation about the elastic modulus of the subgrade as 5,600 psi. So this is a way for us to use the formulas of the to calculate the parameters related to the deflections for the rigid plate under the homogeneous ground. So that's the first method we mentioned, and this only applies for the homogeneous ground. And in reality, when we are talking about the flexible pavement, usually we are talking about a layer system, and there will be multiple layers. In that sense, the homogeneous assumptions about the pavement layers will be not reasonable. So we need to think about the impact of different layers. The next one I'm going to introduce is called the Burmester Theory, which can be applied to estimate the stress and strain for a two-layer system. Well, in the this theory is actually developed based on the theory of the elasticity, and also we have made some assumptions. First of all, we assume that the all the layers for the two-layer system, both layers are homogeneous and isotropic, linearly elastic. This indicates that the features in each layer will be the same. They have the same modulus of elasticity. They have same Poisson's ratio, but for the two layers, they will have clearly have different values. So for the pavement layer, that could be E1, mu1, and for the subgrade, it could be E2, mu2. Those could be different values. Also, in this theory, it assumes that the bottom layer is semi-infinite, which indicates that the bottom layer is usually assumed to be in a subgrade. We know the depth of the pavement layer, and for the subgrade, we don't have any assumptions about where the bottom of the subgrade is. And so in addition, we just assume that all the load, we only have the circular load applied to the pavement structure. And in addition, for the pavement layer and the subgrade layer, they have the full contact and bonding between these two layers, and there isn't any gap between these two layers. So this would be all the assumptions for us to deploy the Burmester theory. This is actually one special case for the multi-layer elastic theory. With this, if we go to check the multi-layer theory, we will consider more than two layers. So now let's go to see how we're going to use this Burmester theory to estimate the stress and strain under the two-layered pavement structure. So first, for the vertical stress, assuming that you are provided with the load or the contact pressure, which is the Q from the tire, and you also know the properties of each layer, elastic modulus, Poisson's ratio, and the thickness of the pavement layer, which would be the depth from the surface to the intersection between the pavement and the subgrade. And usually we can find that if just behind for the center line, just behind under the center line of the contact area, which means that R equal to 0, the this just indicates the center line. Then the ratio between the vertical stress and the contact pressure is a function of three variables. First one is the ratio between the depths. Hz is the depth. And between the depths and the contact radius. The second one is the ratio between the elastic modulus of the two layers. And the third one would be the ratio between the thickness of the pavement layer. So this is the thickness thickness of the top layer of the pavement layer with respect to the radius of the contact areas. And once you have those three parameters, you can then go to check the graph here to find out the value of sigma z divided by q with respect to different depths and the different ratio of the modulus elasticity. So here, let's go to see in this figure actually shows the situation with mu equal to 0.5 and the ratio H1 and A equal to 1, and say that if we have the modulus of the thickness of 2A, which say that is ZOA equal to 2, and if we can find out the ratio between the two elastic modulus, say if it's a 10, then you can easily find out the ratio of sigma z and q will be around 0.117, something like that. So that's the way for us to estimate the vertical stress from the Burmester theory. And we can also identify the vertical stress, which would be the vertical interface stress. That will be the vertical stress at the interface of the pavement structure and the subgrade layer. So which would be the point A in this graph. And the figure here will shows the relationship between the vertical interface stress with respect to the thickness of the pavement layer. And here sigma c will be the vertical interface stress. So this is a sigma c. And this figure actually only applies for the situation with the Poisson's ratio of 0.5. And you can see that by increasing the value of E1 over E2, the value of sigma c divided by q will be smaller, which means that the vertical stress applied to the subgrade, to the interface of the subgrade will be smaller. So that means sigma c will be smaller. But if you decrease the value of H0, H1, increase the value of H1, which means that you're going to decrease the value of A divided by H1, and you can still observe the reductions about the value of sigma c, which means that increasing H1, increasing the thickness of the pavement structure, can also help you to reduce the stress, the vertical stress applied at the interface of the subgrade layer. So this actually aligns with our common sense. By increasing E1 indicates that you will make the pavement layer, increase the stiffness of the pavement layer. Increasing thickness means that you will have the larger protection from the pavement layer to the subgrade. And with that, I will also go to check one example. Assuming that we have the circular load with the radius of 6 inches, so we have A equal to 6 inches, and the pressure, the pressure is which is the contact pressure is 80 psi, and this is a two-layer system. We know the subgrade has the elastic modulus of 5,000 psi for the maximum vertical stress that the subgrade can support. It's 8 psi, which means that the all the values sigma c you calculate should be less than 8 psi. Otherwise, it will make the subgrade fail. Make a subgrade fail to support the pavement structure. And now it wants us to calculate the thickness of the pavement structure with respect to two different elastic modulus when E1 equal to 500,000 or to 25,000 psi. So for this one, I will go to calculate the first situation, and then I'll leave the second one for you to work with to find out the thickness. In the first situation, we have E1 equal to 500,000 and E2, which is always 5,000. And with that, we can find out the ratio E1 divided by E2. Clearly, that will be 100. And also, we know the maximum stress, vertical stress at the surface, at the interface of the subgrade is 80 psi, and the contact pressure is 80 psi. So we have sigma c divided by q, that is 8 bar divided by 80 is 0.1. And now we can utilize this information to find out the value of A divided by H1. So go back to this graph. We know the E1 over E2 is 100, which means that we need to choose this figure. And then the next thing we're gonna find is like the value of sigma c divided by q is 0.1. So we're gonna find out the point from the line we just select. That would be the point here, and this one is almost around 1.15. So it gives us the value as A divided by H1 equal to 1.15. And we know the value of A is 6. So it gives us the calculation of H1 equal to 6 divided by 1.15. That is 5.2 inches. So this indicates that the thickness of the pavement structure should be at least 5.2 inches. So that's the first one. And for the second one, I will just leave it for you to do the calculation. What if I have the E1 equal to 25,000? How we can find out the value of the minimum value of H1? Can anyone give me this the result? Any values that you can calculate from it? You might need to use the figure in the previous page, like what I just did, to find out the appropriate value of the A divided by H1. Okay, maybe I will just go through the solution. So first of all, we will do the similar procedure to calculate ratio between E1 and E2. So we have E1 divided by E2 as, in this case, that will be 25,000 divided by 5,000. So that is a 5. And for the ratio of sigma c divided by q is still 0.1. So we have these two values, and then go back to the previous page. We're going to choose the line with the ratio of E1 and E2 as 5. So this is the line we're going to choose. And then we will have the value of the A divided by H1 from this at the ratio of sigma 1 divided by sigma 1 and the Q as 0.1. So this will give you the result as almost 0.4. So what we get is A divided by H1 is 0.4. So you can calculate the value of H1 as A divided by 0.4. A is 6 inches, it gives you the value as 15 inches. This indicates that the thickness in the second situation is much higher than the one in the first situation. well, you will have the much stiffer materials for the pavement structure. So if the stiffness of your material is small, then you need to increase the thickness of the structure to ensure that the subgrade can support a sufficient amount of the vertical stress. So that's the first one. And then for this two-layer system, we are also able to calculate the vertical surface deflection, which would be the displacement at the surface of the pavement structure. And here we can still use the apply the Burmester theory, and this theory will actually gives you the relationship between the deflection factor F2 and the ratio of H1 and A. And also for in this graph, each line represents one ratio of E1 and E2. Basically, if you are provided with the thickness and the radius of the contact area, you can then specify in the line based on the E1 and E2. And for example, if say it's 100 and with H1 A as 3, then you can get the deflection factor as, well, in this case as 0.085. And the F2 here is just one deflection factor. You can calculate the surface deflection with this equation, where omega W0 is 1.5 times QA divided by E2 times F2. So this is for the flexible pavement. For the rigid pavement, you have the similar relationship as what I showed previously. For the rigid pavement, it's only 0.79 of the deflection, surface deflection. For the flexible pavement, that would be 1.18 times QA divided by E2 times F2. So in general, to find out the vertical surface deflection, you need to get the value of H1 divided by A. You need to find out E1 divided by E2. And this one will give you the value of F2. And then you can find out the value of omega W0. This is only for the flexible pavement. And then you can go to get the value of the rigid pavement. Again, this is only applied for the materials with the Poisson's ratio of 0.5. And here's another example for us to calculate the use this graph to calculate the vertical deflection, surface deflection. And this problem indicates that we have the load plate applied on the road, and the load is 2,000 pounds, and the diameters of the plate is 12 inches, and the layer 1 has a thickness of 8 inches. We know the Poisson's ratio is 0.5 for both layers, and we don't know the value of the elastic modulus for the top layer. And for the surface deflection, what we observe is 0.1 inch. Then we need to calculate what's the elastic modulus of the layer 1. So to do that, we first need to calculate the deflection, the contact pressure. So the contact pressure is the load, as a load divided by the contact area. For this problem, the load is 20,000. The contact pressure, the contact area is pi times A square, and here A is just half of the diameter, that is 6 inches. And this one will give you the contact pressure as 176.8 psi. So that's the first part. And we also know the ratio of H1 divided by A. So this is H1 is 8 inches, 8 is 6 inches, and that gives you the value as 133. And for the deflection at the surface of the pavement, we know the value is 0.1 inch. This is provided by the problem. And we also know that this is a rigid plate, so we have the formula as 1.18 times QA divided by E2 times F2. We know the value of Q. We know the value of Q, which is 176.8. A is 6 inches. For E2 is 6,400 psi. So with this one, we can find the value of F2 as 0.511. So this would be the two values we're going to use. F2 is 0.511 and H1 over A is 133. So you go back to the previous page. We have the H1 over H1 over A is 1.33. That will be some value around here. And for the value of F2, this is 0.511. So you can find out some value around here. And so based on these 2 points, we can then find out the approximate line to represent the ratio of E1 and E2. In this case, that will be 5. So what we get from these two values, E1 over E2 equal to 5, and that gives you the value of E1 equal to 32,000 psi. So that's how we're gonna use the Burmester theory to analyze the variables related to the vertical surface deflection. And another thing we will go through is the maximum tensor strand, which can support at the bottom of the first layer. That will be the tensor strand at the point at the interface between layer 1 and layer 2. And this one can also be obtained from the figure in this page. For the tensor strand at point A is a function of Q, the elastic modulus, and also the strand factor. So the strand factor Fe can be determined by this graph. To use this graph, you still need to know 2 variables. The first one is the ratio between E1 and E2, and the second one is the ratio H1 and A, the thickness and the radius of the contact area. And once you have identified the 2 lines, for example, if you know the value of E1 over E2 is 50, then you're going to choose this line. This is the line I'm going to use. And if you know the ratio of H1 and A is 2, then you're going to choose this line. And the intersection of these 2 lines would be the point for you to identify the value of Fe. For this case, that could be something around the point 55. And then you can use the this equation to calculate the maximum tensor strand applied at point A. So this is the simple method to calculate the tensor strand. We will go through the last example about the calculation of the tensor strand. So here we know the load is 9,000 pounds, and which is equivalent to the contact pressure of 67.7 psi. And we want to, we also are provided with the elastic modulus of the two layers. The first one is 150,000, the last second one is 15,000. And the thickness of the pavement is 8. So to get this problem, to find out the maximum strain at the interface of the layer 1, layer 2, we first need to get the ratio of E1 over E2. In this case, E1 is 150,000, E2 is 15,000. So the ratio is 10. And we also need to know the ratio H1 and A. In this problem, we know H1 is 8 inches, but we don't know the value of A. In order to find out the A, we have to go through the load settings. In this case, P equal to 9,000 pounds, and Q equal to 67.7 psi. But we know that there is a relationship between P and Q. So basically, Q equal to P divided by A, and A is the contact area. That is pi times A squared. So with that, we can derive the value of A as 6.5 inches. And if we put the value of A in the ratio H1A, it will give you this the ratio as 1.23. So we can then go to check these two lines. Check the lines from the E1 and E2 and H1 and A to identify the value of FE. First, for the ratio of E1 and E2, which is 10, this one is easy. So we have this line. So this is the line we're going to select with the ratio of 10. And the second one, H1 divided by A is 1.23. So it should be a line just above this line. This line should be the one we select is 1.23. And then you can find out the intersection, and it tells you the approximate value of FE. For this case, it's around 0.72, and this is FE. Finally, we can calculate the value of maximum tensor strain as Q divided by E1 times FE. So for this case, that is 3.25 times 10 to the power of -4. So this is how we're going to calculate how we're going to use the Burmester theory to estimate the vertical stress strain and tensor strain at different locations of the pavement structure with two layers. So with that, I finished the introduction about the Burmester theory. Do you have any questions so far about the this analysis? Okay. If not, we will still have some time, so I will gonna go to the continue the topic about the flexible pavement with a more complicated, more realistic methods to analyze the stress and strain. So here we have a table to summarize the difference between the model assumptions and the realistic materials. For the previous two methods, we introduced the Burmester method and the Pusinesk method. Both of them will have an assumption about the pavement layers. They assume that they will be homogeneous and isotropic. So the properties at different directions in the same layer will be the same. But for the real materials, usually those the layers is not homogeneous and they are anisotropic. So this will increase the difficulty for you to analyze the stress and strain in reality. In addition, for the elastic modulus, we in the model we assume is constant, but in reality, as determined by a lot of factors, by the stress and the strain, the vertical stress and shear normal stress and shear stress, and also the load applied to the pavement structure. In addition, for the tensor stress, for the model we don't set any limitations about the tensor stress, so they can apply as large as possible, but there might be some maximum values we can calculate. But for the real materials, usually the soil does not have any capability to extend, so the tensor strain will be very small, and we will have some limitations for you to to set the tensor strain. Finally, for multiple layers, for the pavement with multiple layers, in the model we don't assume there's any slippage between the layers, but the slippage happens a lot in reality. Like the location, the upper layers will be shifted to the left, to the front, or to the back, based depending on the traffic load. So this will be a clear difference between the theoretical result and the real materials. This figure actually shows the distributions of the stress that we estimated from the Burmester theory compared with the actual materials, the limestone, the gravel, and the sand. And the red one is the estimation from the Burmester solution. You can see that they will have the similar trend, like by increasing the distance to the center line, the stress will reduce a lot. The pattern will be the same, but the absolute value will be very different. So the some of them could be large, some of them could be small, depending on the type of the materials you're going to select. Also, so with that, when we analyze the stress and strain, we have to clearly understand what's the assumptions we made in order to use these equations, to use those figures for the estimation of the stress and the strain. We can summarize all the methods that we proposed previously as the Oldmax approach. And the Burmester solution and the Burmester theory would be two kind of special case. For the Burmester solution, is in a one layer approximation, assuming that the all the layers in the pavement would be homogeneous. We only have a constant elastic modulus, and we have the constant Poisson's ratio, and so on. For the Burmester theory, it applies for a two-layered pavement structure. So it's still an approximation. Assuming that the pavement structure is one layer, the subgrade is another layer, and this one is actually estimated. The estimation is based on the elastic theory, and the actual Oldmax approach will usually transfer the two-layer system into an equivalent single-layer system. So with that, we can then use the Burmester solution to calculate the stress and strain at any locations in the pavement structure, just based on the equivalency of the one layer to the bottom layers. So I'll give you more details about how to do the equivalency, to the conversion. So first of all, let's consider a two-layer system. For any two-layer system, here you can see the distribution, the load applied to a circular area with a radius of A, and we also know the stress applied. And if there's no two layers, we say that we have the pavement layer with E1 and mu. We have the subgrade layer with ES and mu. So the modulus elasticity will be clearly different. We also know the thickness of the pavement layer, that is H. With that, we can actually measure the stiffness of the pavement structure. That will be E1 times H cube divided by 12 times 1 minus mu square. But with the automatic approach, we want to convert the first one, the first layer to an equivalent layer, which will have the same stiffness, but the thickness will be different. Instead of the true thickness of H, we will have the equivalent thickness of HE. But with this kind of chain conversion, the elastic modulus will be the same to the lower layer. So for both layers, they have the elastic modulus of ES. With that, you can consider all these parts would be in the one homogeneous layer. And you just have the modified thickness of the top layer. And then we can use the Boussinesq equation to estimate the deflections and vertical stress at any point of this pavement structure. And so as we say that the equivalent layer should have the same stiffness of the original layer, and we have the formula to show the to define the stiffness. And this part shows the estimation of the stiffness for the original structure, and this part shows the estimation under the equivalent structure. And here you can see that the only difference would be a part on the top. So what you're going to observe is like for the if you do the conversion, you can find that HE equal to H times E1 divided by ES to the power of 1/3. So this is the theoretical equivalency, but in reality, as due to the nonlinear relationship of the material properties, we usually add one coefficient 0.9 to do the correction about the equivalency. So we try to make the equivalent thickness smaller. With this correction, it will be much closer to the realistic situations. So I guess we almost run out of time today. So I will stop here, and in the next lecture, we will introduce more details about how to use this automatic approach to do the conversion, to find out the equivalent layers, and to estimate the stress and deflections at different locations of the pavement structure, as well as to find out the maximum values of the deflections and maximum stress and strain. So I think that will be all today. Do you have any questions before I close the meeting?
Yes, I think the uploaded notes are the same as the note 20.
Oh, it's
at least the one I downloaded.
Okay, let me double check this one. It's you mean the node 21 is not uploaded?
You opened right now are not online.
Okay, I will double check that one, and then we send you the updated notes. It might be some system error, or I just dragging wrong files.
Yes, thank you.
Great. Thank you for the notification. You can check it later after several minutes. Yeah. If there's no question, I will close the meeting. Just feel free to let me know if you have any questions about the homework assignment or about the class. Good. Okay, thank you very much for your attendance, and I will see you next week.